Hello, my name is Tigran Ishkhanyan. I am from Wolfram Research. My talk is about mathematical functions and new developments there, about Hoyne functions, holonomic evaluator, and about classical mathematical functions.
Good afternoon. My name is Tigran Ishkhanyan. And today I will talk about mathematical functions. First, I would like to thank Devendra for a presentation of myself during his talk. Okay, what's new in Wolfram language 12.0, 12.1 from the point of view of mathematical functions? So first direction is an improvement of what we have. Of course, improvement of documentation pages. 250 plus mathematical functions. Documentation pages were updated. First focusing on the scope section in 12.0 and then basic examples section in 12.1. We can check, just take a look on some of the functions. For example, let's go to something like logarithmic function, yeah? And there is a details section, yeah? Basic examples are similar for all the mathematical functions, including special functions, trigonometrical functions, and others. So there are examples like complex plot 3D and others, like the newest features that we have. Larger, yes, sorry. This is okay? Okay. And all the basic parts for all the functions are similar. They are looking the same. And also, the scope section is standardized now. So we have standard features for all the mathematical functions now. So if you will take a look on documentation pages for these 250 plus functions, you will see the same structure for all the documentation pages. Okay, let's go back to this. And the second direction is of course, development direction. So what we here have, of course, a very big developments in asymptotics part. 5 new Hoyne functions with their primes. They have been implemented in 12.1, so they will appear soon. They are documented, they are tested, and something like this. So in fact, there are 10 functions, 5 standing for the Hoyne functions itself, and 5 for their primes. And also, we are now working on holonomic functions. We are redesigning the algorithms for the holonomic functions, and they will appear after. And let's talk about the general overview on mathematical functions. So the key idea that we are working with is that most of the mathematical functions are solutions of different differential equations. This is the case for the elementary functions, so we can just take a look on this. Yeah, so differential equations are generating as a solutions some functions. Bessel and related functions, of course, the same situation, so we can just dissolve it. And for example, this equation is generating Bessel G and Bessel Y functions. For the orthogonal polynomials, we have the same situation. So you can see the solution of this differential equation. And the last one here, for example, hypergeometric 1f1 and Hermite functions. So they are somehow connected with this differential equation. They are solving this differential equation. Okay, sorry, there is some problem with this, but okay, the next set of functions is a hypergeometric class of functions. For example, 0f1, 1f1, or 2f1 functions. Yeah. So the 0f1 function is the solution of this differential equation. So if we'll write down this differential equation, you can find it in the documentation page. You will get the solution in 0f1 hypergeometric 0f1 functions. However, if you will not make here a full simplification, you will receive the following. So there is a connection between hypergeometric functions and, for example, Bessel functions. Yeah. In fact, there are connections between all of these special functions and the elementary functions. For example, let's try to solve this equation. This is an equation with singular point 0 and infinity. So in fact, if you will write down dissolve with this, you will receive hypergeometric unit Laguerre function. But originally, this is a differential equation for hypergeometric 1f1 function. If you will take the hypergeometric 1f1 function, directly substitute it into the equation, you will receive a 0. So let's check it. That really, this equation is solved by hypergeometric 1f1 function. However, we can also construct solutions in other mathematical functions. About 2f1 function, Okay, so here is the canonical equation of hypergeometric function, Gauss hypergeometric function. And there are two fundamental solutions. Yeah, the first one is a pure hypergeometric function. The second one is hypergeometric function with some prefactor. So, and the general remark here is that hypergeometric functions are very popular and they are very well known in physics. They are very well used in physics. And of course, after update of documentation pages, you can find a lot of examples of concrete applications in the documentation pages. Okay, this is about hypergeometric functions, but there are also advanced special functions. For example, Mathieu functions or Mathieu functions. These functions are solving the following differential equation. So you can write down this equation in its algebraic form and solve it. And these functions are important because they are solving the Schrödinger equation for periodic potentials. So if you write down the Schrödinger equation and just dissolve it, you will receive the following solution. The next set is about the spheroidal functions. So there is a spheroidal equation that is a rather popular equation, and it's solved by spheroidal PS and spheroidal QS functions. You can also construct another solution using spheroidal S1 and S2 functions. However, these are the main functions. And the spheroidals are connected with the Legendre functions. So we can see that if this third parameter is 0, then we are directly receiving more simpler functions. Yeah. Okay, so and the last one is Lamé equation. So there is an equation like this. It's a very hard equation. So there are, in Wolfram language, there are no functions that are solving this equation. There weren't functions that were solving this equation because now we have them. And if you will dissolve this equation, you will receive an object that is called differential root, but we will talk about this later. Okay, so what's the idea of this overview? There are a lot of mathematical functions. Yeah, there is a set of special functions. And we are working with them from the point of view of generating differential equations. And here is what we are doing now. We are making the next step. So what's new in Wolfram language 12.1? This is the new step. This is about Hoyne functions. Okay, so overview, general, 10 new Hoyne functions. Yeah. This is a new step in the theory of special functions. I will explain it later. Hoyne functions are generalizing the hypergeometric class of functions directly. Also, Hoyne functions are much more general than the spheroidal ones, Lamé functions, say, Mathieu functions. And Hoyne functions now are, they have rising popularity in physics, for example, in the theory of black holes, quantum physics, and others. So they are important from the physical point of view. However, we are implementing them only now. Okay, so the general Hoyne equation is an equation of this form. It has 4 regular singular points. So 0, 1, a, and infinity. The Hoyne G, the function that we've implemented, is solving this equation. And also we've implemented the prime function for this. I will explain why we need a prime function. For the case of hypergeometric functions, the derivative of hypergeometric function is a hypergeometric function, just of shifted arguments, parameters. Sorry, parameters, not argument. For the Hoyne functions, we have a different situation. The derivative of Hoyne function is a function of another class. It's more difficult function. And because of this, we have implemented the pair of functions, Hoyne G and Hoyne G prime, like for the spheroidal PS and spheroidal PS prime, because the prime functions are not the functions of the same class. So there is a plot of Hoyne function for some set of parameters. Hoyne function is, okay, sorry, there's a problem of template. So let's take a look on the hypergeometric equation. It's written down here. This is the Hoyne equation. And we can see that we are just adding one more term here, so adding one more singularity. And this is this is what we are making. We are making the next step. We are just taking one more term and trying to solve the equation, yeah? So, of course, the solutions of Hoyne equations equation, they include the hypergeometric functions. Also, Hoyne function is a generalization of a Lamé equation. So let's take a look on this. So this is a Hoyne function. This is a Hoyne equation, sorry, and this is the Lamé equation. Yeah. So Lamé equation is just a specified Hoyne equation with specified parameters. Okay, what about Hoyne G? So Hoyne G is just the simplest solution of this equation. Another second fundamental solution is written using also Hoyne G functions. Let's take a look on a special cases of Hoyne G. I will make it bigger. Okay, so 2f1 function itself is a specific case of Hoyne G. So we can see here that we are just specifying the parameters of Hoyne G, and this is hypergeometric 2f1 function. There are two possibilities. Also, of course, Hoyne G can generalize other functions from the list of mathematical functions. Also, now we are able to solve the Lamé equation in terms of Hoyne G. So this is the equation that wasn't solved in Mathematica. Now we can write down the solution, the general solution of this equation in terms of Hoyne G, and work with it because this is a full function, I mean complete function. We can work with it, we can differentiate it, we can substitute somewhere. Yeah? This is something new. And also about importance in physics. For example, this infinite potential is solved in Hoyne G function. This is a new potential. In fact, it was derived maybe 2 years ago. So here is the solution, fundamental solution. It's not the wave functions, it's a fundamental solution. And in terms of Hoyne G, multiplied with some very big prefactor. However, if we will substitute this to Schrödinger equation, we'll receive that it's true. Really, this function is solving the Schrödinger equation. So this is something new. This is some new subject in mathematics, this Hoyne function, Hoyne G function. And it can be successfully applied to some physical problems already now. And because of this, we are implementing these functions. Okay, as for the hypergeometric functions, we have one major function called hypergeometric 2f1 function and have confluent forms of it. This is the same. We have the same situation with the Hoyne functions. So there is a general Hoyne equation, and there are confluent Hoyne equations that are generating confluent Hoyne functions. So they are written here. This is the general Hoyne equation with 4 regular singular points, 0, 1, a, and infinity. And here are the 4 confluent forms of Hoyne equation. This is called confluent Hoyne. This is double confluent Hoyne. It has 2 irregular singular points located at 0 and infinity. This is called biconfluent Hoyne equation. It has 1 regular singular point at 0 and 1 irregular singular point at infinity. And there is the last equation, triconfluent Hoyne equation, that has only 1 irregular singular point, it's in infinity. And this equation is a generalization of area equation, for example. The structure is the same. Okay, let's take a look on this one. So okay, what's the problem? Okay, here it is. Confluent Hoyne function, a confluent Hoyne equation. 2 functions, Hoyne C and Hoyne C prime, standing for the confluent Hoyne function and its derivative. This is some plot of it. What is it? Hoyne C is generalizing the following functions. So it can generalize 2f1 function itself, 1f1, and also Mathieu function. We have derived these formulas recently. And so Hoyne C is a very important function from a mathematical point of view because it's a very good generalization of all the hypergeometric class of functions plus advanced special functions. Also, Hoyne C is able to solve the spheroidal equation in its general form. So there is a spheroidal equation, and there is a parameter lambda that if we will choose it to be spheroidal eigenvalue, then this equation will be solved in spheroidal functions, spheroidal PS or QS. But what if lambda is arbitrary? And in this case, we are able to solve it using Hoyne C functions and work with it, of course. So Hoyne C is rather important because it's it has the biggest potential in the Hoyne functions, I think. The double confluent function is much more difficult because it has only irregular. I mean, the set of singular points is irregular, 0 and infinity. And because of this, we don't know what to do with this function. I mean, in general, how to construct the solutions, good solutions in these singular points, because it's impossible. However, we've implemented two functions, HoinD and HoinD prime, that are solving this. The whole HoinD is solving this equation. B-confluent Hoin function is a HoinB function that solves this equation. It's generalized the 1f1 function, 0f1 function, and it's of course connected with the Bessel functions. So HoinB is rather useful in quantum mechanics already at the moment because there are a lot of articles on this. How can we solve different quantum mechanical problems in terms of HoinB function? So for example, if we are taking a doubly anharmonic oscillator potential like this, let's plot it. So this is a potential like this. We are able to construct the rather simple solution in terms of HoinB functions. Here it is. And we are able to verify that it's really solving the Schrödinger equation symbolically. Second example from quantum mechanics is the following. So there is a class of potentials like this. So here is the plot. And we are able to solve it using also HoinB functions. And here is the solution. So this is a rather, say, complex potential. However, we are able to solve it in Hoin functions. OK, and the last confluent Hoin function is called triconfluent Hoin function. Hoin T solves this equation that has irregular singular point at infinity. This is a generalization of Airy equation, in fact. And of course, Hoin T solves the Airy equation. If we will just substitute this Hoin T with specified parameters into Airy equation, we'll receive a 0, of course. OK, Hoin T is important from both classical and quantum mechanics point of view. So we are able to solve this type of equations in Hoin T. So it's a classical anharmonic oscillator. It's solved in Hoin T, and we can work with it. We can simulate the dynamics. We are able to also solve some solutions from quantum mechanics. In fact, it's the same potential, fourth order polynomial potential, and we are able to solve it in Hoin T functions. Yeah. And also very surprising, we have a very surprising result that when we're implementing these Hoin functions, we're thinking that Hoin functions will be the most important ones. However, we found out one very beautiful example from quantum mechanics, how we can use also prime functions. So let me show this example. OK, so there is a potential, a recent potential, like this, inverse square root. And surprisingly, so it's a singular potential like this. And surprisingly, it's solved in Hoin T prime functions. So this is a very original result. And this is showing why that our implementation is useful. So here is the solution, the two fundamental solutions, and we are just substituting and receiving a 0. So I mean, these solutions are solving the equation. And this is a rather good result. And in fact, you can find all these examples in the documentation pages of Hoin functions, because the documentation pages of Hoin functions are similar to all the other mathematical function documentation pages, because we have some standards, and we are making everything to be similar to this. OK, so this was about Hoin functions that will appear in 12.1 soon. What else? What we are working now at the moment? So we are working on the next step of theory of special functions, the general holonomic evaluator. At the moment, we have two functions, differential root and difference root in Wolfram language. Yeah. Differential root is a function that you can use to define your own special function. So you are giving just some differential equation, some initial points and values, initial point and values, and differential root is able to numerically construct some function that is a solution of this differential equation with these initial values. OK, however, at the moment, differential root is using not a very good scheme because it's using n-dissolve. So it's using numerical integration scheme, but it's not very good from the point of view of special functions, because in special functions theory, we have a Frobenius theory that is able to construct all the solutions in power series. So at the moment we are implementing a new evaluation scheme for differential root that will be based on series expansions and analytic continuation procedure. In fact, this is done already. We have also totally updated all the documentation pages for differential root and difference root with a very big set of examples, but they will not appear in 12.1. They will appear in 12.2, I think. And the next step that we are now working is our optimized algorithms for these holonomic evaluators, because series-based analytic continuation scheme is good, but it's not very fast. It's faster than the current differential root. However, it's not the optimal one. And because of this, we are trying to now implement this fast summation algorithms like rectangular splitting, binary splitting, and others to the differential root. Okay, so this is all on mathematical functions. I would like to make just a small summary. So in fact, we have fully updated documentation pages for all the mathematical functions, 250 plus functions, 252, I think. Then we have implemented 10 new Hoyne functions and also designed some examples how we can use them, like in physics, in classical mechanics or quantum mechanics. And at the moment, we are working on the improvements of holonomic evaluators. So this is all. Thank you for your attention, and I'm ready to answer all the questions that you have.